Our next speaker is Mark Vanderland. He's the Jianping Su and Carly Peace Professor of Biostatistics at UC Berkeley. He's won numerous awards, including the 2004 Mortimer Stigland Award and the 2005 COPS Award. He's contributed widely to statistical methodology and genomics, survival analysis, targeted action likelihood estimation, and semi-parametric models, causal inference, data, adaptive loss-based super learning, and multiple testing. Today he'll tell us a little bit about targeted learning.
Thanks so much. It's a real pleasure to be here. I will make a few remarks about some events over the last year in the area of target mix and likelihood estimation of targeted learning. So here's the general story, right? We have kind of causal frameworks which allow us to define causal quantities, which allow us to establish identification results, and thereby define an estimand. Yeah. Then, of course, that's where the sensitivity analysis might come in. Then we need to estimate the estimand. The estimand involves essentially conditional distributions of what happens in the future given the observed past. So we have to learn them. So that's where machine learning comes in. We generally recommend super learning as a way of building an algorithm which is more powerful than any of its ingredients. But that's not enough. We need to do a targeted mix and likelihood step driven by theory, efficiency theory, a so-called canonical gradient, giving us this least favorable model, do a little maximum likelihood, and then suddenly we go from a plug-in estimator which has no asymptotic distribution, generally speaking, to one which is now asymptotically normally distributed, and so we have some, at least, theory. The superlearner is as good as its library, and so we need very good machine learning algorithms. There are a lot, but when you actually look at the theory of machine learning algorithms, there's not always that much known, but either way we thought of a particular machine learning algorithm which is really just maximum likelihood estimation or minimum loss estimation, where you say I want to minimize my empirical mean of like square error, residuals, or whatever loss function you use over all so-called multivariate real-valued catalog functions, right, continuous left-hand limits with some so-called finite sectional variation norm. Any such function can be represented as an infinitesimal linear combination of tensor products of indicator basis functions, like indicator x1 bigger than the cutoff for all cutoffs, and indicator x2 bigger than all cutoffs, bigger than the cutoff for all cutoffs, and then the product, right, and so on. And that means essentially we can do linear combination, like a linear model, and then where the sectional variation norm is nothing else than the L1 norm of this vector of coefficients. That's why we started calling it Lasso, because you can start employing Lasso software to fit these things. Then, of course, you would choose the L1 norm with cross-validation. And interestingly enough, originally we established a rate of convergence which I thought was already remarkable, which was n to the minus 1/4 and a little faster than that, independent for all dimensions. And remember, you're essentially not making any smoothness assumptions, you just assume things are right, continuous left-hand limits, so they can even have jumps. But then, due to Liu, who might be here for a student at Berkeley, who now I think moving to Stanford, he made me aware of an interesting paper in the stat department by Feng et al., who figured out this entropy, like covering number for multivariate cumulative distribution functions. Now, this representation theorem we have for any catalog function with finite sectional variation norm just writes any such function as one big sum of essentially differences of multivariate cumulative distribution functions. You just have to be monotone. So we can actually utilize that result, and now we also have a rate, just like they have, of n to the minus 1/3, and then the only way the dimension kicks in is through log n to the power d. I mean, these rates are remarkable. At the same time, of course, the constant in front of this is a whole different ballgame, and heavily affected potentially by the dimension. If you really do more careful calculations, you can see that the constant is behaving like square root times the dimension, but then the actual sectional variation norm of the true function. So that means the sectional variation of the true function is a very interesting measure of sparsity. People are often using that, right? So if you actually the true function is simpler. In other words, you don't need 10-way interaction or tensor products across 10 basis functions, then, but only up till 2 or 3. Yeah, then you get a much better constant. That constant can be as bad as 2 to the power d, but then depending on the true complexity of the function, it might actually be very good, and it might be square root d. So all that can happen. It just demonstrates that sectional variation norm is a nice non-parametric measure of sparsity. So when you include this guy in the superlearner, you are guaranteed to achieve the same grade, so that is a very helpful thing, and that has immense implications for any kind of double-robust estimator, including target maximum likelihood estimator. That if you start using highly adaptive lasso as a machine learning algorithm for both the G and the Q and the outcome regressions, so both the full data as well as the censoring parts of your procedure, then you're guaranteed to be asymptotically efficient, because the secondary remainder can be bounded through Cauchy-Schwarz by L2 norms, and that's all implied by these results. I'll just give you an example how you can utilize software for it. For example, if you want to estimate a conditional hazard for right-centered survival data, right, then you can write your hazard as an e to the power of some function. So you need a little link function, and then you say that function could be actually anything. So I can just model that with this big linear combination of tensor products of indicators. And then you can actually use software like GLMNet, which also has the Cox link, but you can also use it for logistic and linear and all that. And we can use that, and we just wrote an extra function which allows, builds for you that basis and then does some computationally reasonable things, because utilizing the sparsity of these basis functions. So we can actually do this stuff, even though it's computationally, by the way, quite challenging. So we are definitely having work going on making things more scalable. Because there's no reason that for a finite sample size of a few thousand that you need 20-way indicators like these multi-way. You don't need them, they're mostly zero anyway. So it's just a matter of being smart and figure out a nice screening, and then let cross-validation decide to stop when the complexity is not helping anymore. Okay, this is just, we've done, so this is just what we call in general TMLE as a quick overview, right? You have an initial estimator, you have a canonical gradient for the estimand. The estimand is a functional from the probability distributions in your model to the real line. You can take pairwise derivatives, and you can find the direction in which the estimates increases the steepest, right? And that's called a canonical gradient. And that's also called the efficient impulse curve. Anyway, we have to come up with a submodel which uses offset the initial estimator and then has a score the canonical gradient or spends the canonical gradient, and then you do a little maximum likelihood, and then you get your update, and then you do just your plug-in estimator. And because it's a maximum likelihood, it solves a score equation, so you would have that the empirical mean of the efficient impulse curve equation is solved, and that drives, as we know, asymptotic efficiency and normality. Just a little more about least favorable models. What are they? What's the intuition? The least favorable model. So what you do, you compute this Kramer-Rauer lower bound. This is the Kramer-Rauer lower bound for if you have a one-dimensional parametric model and you estimate a certain function of epsilon. Right? What will be the Kramer-Rauer lower bound? That will be the derivative of that function of epsilon squared divided by the information. And then what you do, you find the worst case, right? The worst parametric model, which makes estimation of this particular function of epsilon, which is our psi, our estimate, most hard. And another way of writing that information, right, is this way, which is the change in the estimate squared divided by the increase in log likelihood. So that's actually quite an interesting thing, right? Because you're trying to say for a unit increase in likelihood, I want to get the maximal change in my estimate, so that all the data is directly translated into fitting the estimate. And that's why you can think of this least favorable model as a model which is really now only concerned about fitting the estimate. And that's why it's so effective in bias reduction. And a local least favorable model means you wanted to have that property locally, but then you might wonder, why only locally? So that was a question I asked myself. Okay, local is nice, right? If, for example, your initial estimate is already very close to the truth, then your maximum likelihood estimate will be close to zero anyway, and then it's enough, and you can prove it's enough, you don't even need to iterate. However, in general, that might not do it. So we actually like to have a model which always has that property, that as I move along this path, wherever I am, if I change my epsilon a little bit, any increase in likelihood gets directly translated into the change in the estimate. So that it remains to have that property. And so that means it needs to satisfy now that the score equals the canonical gradient, not just at epsilon to 0, but at any epsilon. And once you have that, then you also have that in one step, if you do the little MLE, right, you're already solving the efficient inverse curve equation exactly, and so you don't have to iterate. And so that also proves that it really is kind of a very effective parametric model for doing the extra fitting to make the estimator relatively unbiased. You can then recursively find does there exist such a p epsilon, and that's solved by this equation. If you can recursively solve this, if you take the log here of p epsilon, you take the dv epsilon, you get d star p epsilon. This is also just like a differential equation. You can start at p and then you solve for the next p at a little bit, and a p at the 2 little bits, and so on and so on. And in this way, it's just like solving a differential equation. And so this is how you can recursively define this universal least favorable model. However, I think a more intuitive way, at least more pleasant way in practice, is to think of this in terms of a local model. Once you have already a local least favorable model, which has locally this property, then it's actually very intuitive, right? If I'm in the desert, I have to go somewhere and somebody gives me a compass, which I know sucks in general, but it tells me at least how to go in the first meter, right? It only works locally, then I can live with that. Right? Because what I do is I look at my compass, it says go there, I make 1 yard, I stop. Then I look at my compass again, then I make 1 yard, I stop. I just don't use it for 100 yards because then I know I'm probably wasting effort. That's how you can use a local least favorable model. Just walk the path a little bit, change your offset to the new one, walk your path again a little bit, and so on and so on. And that actually is the same formula as you found there, which at the end always gives the same formula. So at the end, that is the solution, but this is a nicer way to think about it, and also a nicer way to implement, I think. So then, this we could only do for 1 parameter. And then I thought, yeah, what about 10 parameters or 100 parameters? And so my idea was, why don't we use a 10-dimensional local least favorable model, which we can do, right? Which has locally at epsilon to 0 has as score the 10-dimensional canonical gradient. And then, you know, let's maximize the likelihood over a Euclidean ball, which is very small, and let's say set it equal to delta, move in that direction, and then that's 1 delta. Then make that your offset, do the same thing again. So every time you maximize your walk likelihood over very small Euclidean balls, and it now becomes like a 1-dimensional model where the delta, 2 delta, 3 delta becomes the tuning parameter, becomes the parameter of this parametric model. And that seemed intuitive to me, except I didn't understand, at the end it looked like a 1-dimensional model. How can I, with a 1-dimensional model, solve 100 score equations? So anyway, here is the model. And this is the 1-dimensional model. It has data dependence in it, and it is of this form. And you can write this p to the exponential. And what is the property of it? If you look at the empirical log likelihood, you take the score, you get the Euclidean norm of the vector empirical mean of the efficient inverse curve. So this means you take the empirical mean of the first efficient inverse curve for the first component of the estimand, square it, take the empirical mean of the second efficient inverse curve, square it, plus third, plus that. So if you solve that, you solve them all. Right? So this is just a 1-dimensional model which happens to have as score this Euclidean norm, and as a result, once you maximize your likelihood, you solve all of them. So this allows us now to start doing targeted maximum likelihood or target minimum loss to target, in fact, infinite dimensional parameters, as long as they're infinite pairwise differentiable parameters. We can target complete survival functions, and this way we get completely compatible plug-in estimators, which applies for all. So that was something we really like to do, and so you can see the benefit of it in this survival analysis setting. Suppose we have right-centered survival data, and we want to estimate the treatment-specific survival curve, right? The survival distribution you would have seen if everybody would have been intervened by through a rule D, and then you can, the identification result and the randomization and censoring, proportionate random, is that it's given by this conditional survival function given treatment and covariates. You set the treatment according to the rule and you take the average. Suppose we want to estimate that. Normally what we did for any particular time point t, we would estimate this treatment-specific survival curve with TMLE, and then for every t we would do it separately. But then you don't necessarily get a momentary survival function, certainly for small sample sizes. So here now we can actually use this universal model and start targeting this whole curve for all time points. What does that mean? That we are going to have an hazard, a conditional hazard. We are going to fit it with superlearning, like including this highly adaptive lasso. So we get a conditional hazard of t given a and w. And then we do this targeting step with that one-dimensional model I wrote down, which changes that hazard, which involves targeting is using this 100-dimensional, let's say we target 100 time points, targets this 100-dimensional survival function, and then that's it. And then it gets an updated conditional hazard, and now you use that hazard for getting the survival at every time point. Right? You take the product integral up till time t of 1 minus the conditional hazard, and you take the average. And so for this problem, we know the efficient impulse curve. It has this form, right? This is kind of a normal, this is like your indicator of an observed failure divided by the intensity, and then here's the covariate in front, right? So for target maximum likelihood, this would become, like if you do logistic regression for the hazard, this will become the clever covariate, and then we can, run a full logistic regression to make sure we solve that component of the efficient impulse curve. And this part we always solve because that's the covariate component that you use in empirical distribution. And so, and you see that clever covariate depends on the propensity score, it depends on the survivor of censoring, and so you need to get that too. So a local least favorable model would be defined by taking a logistic regression for this conditional hazard where you just offset your current fit, your superlearner fit, or your Hall fit, and then you add this time-dependent covariate, and then you can just run pooled logistic regression, just maximum likelihood to fit epsilon. And that, however, we are not going to use this local one, we only use this local one to define our universal one. Right? So that's how we then do it. And so you get then these target maximum likelihood estimators which target the whole curve. And you can see, for example, here in this little example, the iterative TMLE is the black one, which is a little, goes up and down. And if you do the one step, the TMLE, which targets the whole curve, you get this, beautiful kind of smooth thing. And that asymptotically is not going to make any difference, because, who cares? But they're both going to be true at the even root n rate. But the point is, if the sample size gets small or things get just hard, right, then it starts really making a big difference. You get immense gains. This was actually the whole motivation of TMLE originally, right? It had to be a plug-in estimator because then you can utilize global constraints about your data distribution, which asymptotically are negligible, but in finite samples have an immense impact. And this is just another example of that if you push that envelope. Here you see, for example, how you get a relative efficiency of at least 2 relative to doing it separately, still using an efficient estimator like TMLE point-wise, but not utilizing that there is this survival function should be monitored. It should all be compatible with a single targeted hazard. Okay, so that's one story. We're also doing a lot of work on, this kind of multiple bandit problem. This has been going back for some time, but it's still doing interesting work, at least we think interesting work, on these group sequential adaptive designs where you learn from the observed past, the previously enrolled patients, figure out what the optimal individualized treatment rule is, and then set your randomization probabilities for the next group of patients accordingly with a little bit of experimentation. And now, obviously, there's a lot of benefit of these adaptive designs. I mean, we're also thinking about things like, doing this really in continuous time, that we can also learn from lots of subjects. We have been previously enrolled, but we only have data up till not yet the full outcome, but there may be all kinds of surrogate outcomes. So how can we really do this adaptation much more in continuous time? So there's work going on there. But in particular, we have Aurélien, is a PhD student of mine, who also has been working on this braid for the Hall. We have now some new results where, one of the big challenges was you can try to learn your optimal individualized treatment rule, but you always need some experimentation. But you cannot just choose that for the next patient, you have to put a little randomization on top of it. Originally, we could prove all the results we wanted, asymptotic fit. Like we learned the optimal design, and then we also still got normality for the TMLE, because the TMLE removes all the bias due to the randomization problems being known. So that was all good, except we had to stay away from 0. We always needed experimentation delta. And now Orlev figured out how to actually let delta go to 0 and actually go 0 as fast as n to the minus 1/3, which is quite remarkable, so that we can actually truly learn the optimal individualized rule from the past, but actually start also applying it truly, and thereby get a really powerful design. Anyway, we're also doing this stuff for time series. A lot of work. I'm tired. I think it's time. And for the people, we are doing a lot of software development. Just as a final thing, so we are, because this is all using very general functions like superlearner and the targets, that they're just the same things over and over every estimation problem. So the software should be programmed accordingly, so that we don't have all these students or whoever writing their own little RPEGs with their own little methods. And then we don't have guarantee that all the pieces are truly reliable. So that we are now trying to build a really strong, reproducible software environment, and there's lots of work going on there. Thanks again.
Time for a few questions, Mark.
So the universal local model would require solving a differential equation. So do you have particular cases where you can have closed form solution, or you always solve it numerically?
All right. Many of the problems, I mean, many people here have worked in this area, they know this, right? It actually happen to be universal least favorable. So they're closed form. They happen to be universal least favorable. Except, and that happens, for example, if you see that the targeting step involves like a clever covariate, which only depends on G, when your parameter depends on all the other parts of the likelihood. So then you know, in one step you're done, and it is a universal least favorable model. However, there are also lots of examples where that's not the case, and where it is iterative, right? And in these cases, at least we have this differential way, right, of solving it. Can we soon do that somehow in closed format? I think that takes smart people like yourself to figure that out. But many times it's not obvious to me how you would get a closed form out of it. But at least we have the differential equation. Yeah.
Thank you.
Yes, here.
Hi, Mark. I have a question about the claim of the convergence rate of Hal.
Mm-hmm.
Maybe I misunderstood, but were you saying essentially that you're breaking the curse of dimensionality? It's no longer something you have to worry about?
No, I mean, this is something, of course, Jamie and I have talked a lot about. The curse of dimensionality is still present, as it will always be present, but it's in a constant. So the rate is remarkable. The constant, as I was talking about, right, a constant can be as bad as 2 to the power d. But
Right.
if the true function...
Usually people worry about the curse of dimensionality in the rate. So you're saying for this class of models...
The rate is not
solved.
affected by the curse of dimensionality. That's remarkable. Yeah.
So should I think of it as it's a small class of functions relative to the usual class of functions where...
I think it's a pretty big class of functions. Because we're talking here about, take for example, all functions which are multivariate functions and which have a derivative in each component, and the derivatives are bounded. It doesn't matter what the bound is. That is included, just one derivative in each component, is included in this class. This class is much richer because they can even have jumps. It can be discontinuous. So it just happens to be all the penalty is in the constant, not in the rate.
Let's think Mark one more time.